All right, last session of the day. We are going to start with Dr. Tyler Lay. Dr. Lay is an associate professor of civil and environmental engineering at Oklahoma State University. He was a recipient of NSF's prestigious Career Award. His research interests are in the area of concrete materials, 3D chemical mapping of cements and mineral admixtures. It says here he is an outstanding instructor and researcher, and most people know you as just an incredible presenter. Your energy and your fire, and I know you're going to bring it. Let's welcome Dr. Tyler Lay.
Let's get this fired up. Let's see here. Okay. What's that? You should watch out. You never know what's going to happen. Okay, so it's like we're moving here. And how's my voice? Am I okay? Okay. Okay, I would want to say first off, thank you so much for sticking around. This has been a great day so far. And what a beautiful surroundings we have. Have you noticed all the beautiful art we have on the walls? The beautiful orange coloring? It's paradise, right? Paradise. My name is Tyler Lay. I'm from Oklahoma State University, and this has been a very, very long endeavor that I'm talking about. This project I've been working on and off, not constantly, on and off for over 8 years now. And anyone that knows that's worked on a very, very long, very, very challenging project knows that it takes a team. It takes a real team to make these things happen. And I have a whole team of graduate students listed up here that have all done some very, 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 very great work on this project. Could not have done it without them. In addition to that team, I need to thank the folks that believed in me, that funded my early research project in this, because this is a little bit out of the ordinary. And Oklahoma Transportation Center, Concrete Pavement Technology Center, and Portland Cement Association, and this work started right here in Oklahoma, and we should be proud of that. Really, really proud of that. Ongoing right now is actually the first Oklahoma-led pool fund study, again, by research developed right here at Oklahoma State University. And ODOT should be very proud that these states have decided to join them and to fund this research. And I want to especially thank the folks here, and especially Ron Curb. Ron, this work could not have happened without you. I really appreciate it. But all these folks here on the whole research team made this possible. Okay, thanks a bunch for you guys. Now I'm going to talk about some basics. I'm going to talk about the basics of air and train concrete. Something talked about, again, a new meter, something called the super air meter, and then the future, right? Now we're going to be talking about concrete. In my opinion, it's the greatest material on the face of the earth. And Jeff Voles and I will battle anyone in a battle royale that says differently, okay? We love concrete. We know that the ingredients in concrete are rock, sand, cement, and water. And actually the last ingredient is love. You just got to whisper some sweet words to that concrete right as you're making it. That's the secret, okay? If it's not working, just whisper some sweet words to it. But you need one more ingredient if you want air and train concrete. One more ingredient. You need soap, okay? And I'm showing Dawn dish soap up here, and you can actually use Dawn dish soap to air and train your concrete. And you think, well, why would you do that? Well, your hands smell great, okay? But it doesn't really help your freeze-thaw durability, and that's what I'm going to be talking about today. Why would we ever add air to concrete, right? Because when you add air is not very strong. All of my students know this. They've all heard that from me before. Air is not very strong, so why would you add something that's not very strong to your concrete? Well, these bubbles happen to be the key to the freeze-thaw resistance of the concrete. The key. And as we talked previously, weather's a big thing here in Oklahoma. Freezing and thawing is definitely a big thing, and we need these air and train bubbles. This is really important, ladies and gentlemen. This is a new kind of concept. Air volume does not necessarily equal freeze-thaw performance. I'll say that again. Air volume does not necessarily equal freeze-thaw performance, and I'll be proving you to that today. And the smaller bubbles in our concrete are much more effective in providing freeze-thaw resistance than our larger bubbles. So how much air do we need? And most people know. Most people that are in the field, most people that have dealt with concrete, they just know you need about 6%. You need about 6% air. That's the old tried and true concept, the old tried and true manner that was developed in the 1950s off 3 mix designs with 1 cement and 1 admixture. It's not the same world we live in today, ladies and gentlemen. We live in a very, very complex world. We're going to talk about that coming up. The current ways to measure air inside concrete are usually one of these three methods: the pressure meter, the rollometer, or the unit weight, and most commonly, it's the pressure meter. We're going to be talking a lot about the pressure meter today, and actually an update to the pressure meter. But the biggest problem with all three of these methods is that they only measure volume, and volume is not enough. It's not enough. So what do you want in an air void system? Well, I'm showing two air void systems here, one on the left and one on the right, and both of them provide the same volume of air, the same volume. But I'm telling you, you want the one on the right. And why? Because if I'm a water molecule and I'm in the paste, I'm in the cement that's hydrated, and I'm freeze, and I try to turn to ice, there's a 9% volume change that actually tries to occur, and that water tries to escape. It tries to move from the paste to a void. And every single void can protect a certain area around it, right? It's like man-to-man defense, right? Protects a certain area around it, right? And you get much, much more protection out of the air void system on the right than you do out of the air void system on the left. That's why we want small, well-distributed bubbles inside of our concrete. Again, both of them have the same volume, but they don't have the same performance. Hope that makes sense. Now, how would I get this? How would I find out what my spacing of my bubbles are? Well, right now, the only way to do that is to take hardened concrete, to cut it up, to polish it, and to look at it underneath the microscope and actually run a linear traverse through it, and you count the bubbles. Oh my gosh, how boring is that, right? Yes. It kind of sounds exciting, but I'm kind of weird, I know. Takes a long time to do this, right? But with this technique, you get something out called the spacing factor. Ooh, doesn't that sound impressive? Okay, what the spacing factor is a roundabout way to talk about the bubble spacing. And just real simply, it takes the real bubble distribution or some concept of the real bubble distribution and makes an average size bubble averagely spaced in the paste, and then it takes the average distance between them. So it's an average of an average of an average, right? In the end, it tells us something about the bubble distribution inside of our concrete, and it works pretty well. And if we didn't understand anything I just said, that's okay. You should know that the spacing factor you want is 0.008 inches. That's the number you want. That's the magic number. All right. Great. And the way to really test this is with something called the rapid freeze thaw testing. Notice I have the terms rapid in quotes because it's very rapid in terms of geologic time, but it's not rapid in terms of human time. It takes about 3.5 months to run this test, and we cannot wait to decide if that's good concrete or not until 3.5 months after it's been placed. That's just not acceptable. But that's the tried and true method. Now, if we can summarize all this, we've got these pressure meter tests, these tests that don't take very long. They take minutes, and they give you total air volume. We've got this hardened air void analysis test, this microscope test. It takes 7 to 14 days because you have to cut the concrete, polish it, but it tells you something truly about the air void system. We have this rapid freeze thaw. It takes 3 months. This is maybe the best of all of them, but we can't wait 3 months. So what does everyone use? The test that takes minutes. We have to make decisions now, right? Got to make decisions now about our concrete. We have to decide it immediately. Is it good or is it not? What's going on? Now, let me just show you this in another way. Maybe there might be a few skeptics out there when I say that our modern concrete mixtures are a little bit different than our old ones. And this is a very old school mixture. This concrete mixture only has one admixture in it, an air entraining admixture. That's it. And we can notice we got this magic spacing factor. That's the magic number. I'm showing you 008. That's the number you want. And when you get enough air inside your concrete, you're good. 6% worked well. That meets specifications. Everyone's happy. Everything's good. The world's a good place. Now let's bring in the bad news. If we bring in a mixture with a high-range water reducer in it, how often are those used these days? A lot. Well, when you start to combine admixtures inside your concrete, you'll find out that 6% air doesn't work well anymore. 6% air doesn't provide us the spacing of the bubbles that we need for freeze-thaw performance, and I'll prove that to you coming up. And you need something like 9% air sometimes. In some mixes, it's 7. In some mixes, it's 10. Air by itself, air volume by itself is not enough, and I call this the yikes graph. Because for specification writers, this is the scary one. Okay, this is a really scary one because you have no idea what concrete mixture they're going to use when they go to build your job. You can just tell them how much volume of air right now, and we need to do better than that, and we will. Let me show you a bit more data. If I show air content down here on the x-axis, I show this spacing factor number, and this is this magic number, 008. And now I'm showing you data that if it's an open dot, these are the open ones, that means it failed the freeze-thaw test. And if it's a closed dot, that means it passed the freeze-thaw test. And this is mixtures with just air entrainers, the old school, okay? The easy ones. And if you start to bring in mixtures with high-range water reducers in them, they start to look like this, and it might be a bit hard to see, but this is the one. These two data points right here should make every highway official, every single that's an owner of concrete infrastructure go, because these mixtures would pass every specification in America, yet they're failing the freeze-thaw test. So why does this happen? What's going on here? Why does this occur? Well, remember that hardened air void analysis? We can actually go through it. Instead of just using one number, we can look at the distribution of the bubbles. And what you'll see, this is the bubble size down here, and this is the frequency, or how often they occur. They're small voids, and this is the mixture with just an air entrainer, old school. And look at that. We get a bunch of small voids. That's good. And look at the new mixture, the ones with the combination of admixtures. We get a bunch of big voids. That's bad. It's that simple, ladies and gentlemen. Good and bad. Okay? That's what we want to. Air volume is no longer enough. So in summary, it's common to require a certain volume of air in concrete in order to obtain freeze-thaw durability. But this volume of air does not equal air void system quality. It does not equal freeze-thaw performance. And although we can run hardened air void analysis, it's just not practical to run that all the time. It's not. So what do we need? Well, we need a test that can quantify air void systems quickly in fresh concrete. We need a test that can investigate a sample of significant size that's economical and field ready. And ladies and gentlemen, I want to introduce and talk to you about the super air meter. And what it is a typical air meter, but we've modified it so it can hold higher pressures. We've actually replaced the typical dial gauge with an actual digital one, and the test is going to end up taking 8 minutes to run, which is a little bit longer than the actual typical one, but that's okay. I'll talk more about that coming up. And this is what it looks like, and I'm actually lucky to have one right here in front of you today, so you can come and look at it if you want later on. And if we notice the label is orange, oh, strikingly orange. What a beautiful color. That's on purpose. And no, it doesn't come in Sooner Red. The digital gauge on top is really cool. This gauge is amazing. This gauge is something we developed at Oklahoma State, or worked with other folks to develop. This gauge will tell the operator how to run the test. It watches the operator run the test and will void it if they run it incorrectly. And then it gives you all the calculations and gives you two numbers. The air content, same number we're used to getting, is something called the SAM number, which I'm going to talk about coming up. So this digital gauge is really, really, really important. And everything here, you can learn more about on this website, superairmeter.com. So how does it work? Well, you fill the bottom bowl in the same way you always would. No difference. 3 layers, 25 rods each one, tap it with the hammer, put the lid on it, add the water through the petcocks, the same way we always run an air meter test. And we're going to be talking about what goes on in the top chamber and the bottom chamber. Top chamber's up here, bottom chamber's where your concrete goes. This is where the actual water is. Okay, this is just kind of an idea how the test runs. This is pressure, and this is time. Top chamber, you increase the pressure. The bottom chamber's at atmospheric. You hit the lever, smack it with the hammer, and that's the typical way to run a pressure meter test. This is the standard way, okay? For you concrete people out there, you know what I'm talking about. For you don't, if you don't, good luck to you. And then we run the test again without releasing the petcocks, and then again, and we get a curve. And then we're going to release the petcocks, take it back down to atmospheric pressure, and we're going to run the test again, and we get 2 curves. And we're going to compare the first curve to the second curve. And most folks in this room, it probably look pretty similar, but if you look very, very carefully, there's distinct differences, and those differences between the curves is a great insight to the air void system. inside your concrete. And I'll talk more about that coming up. We're going to use an algorithm to calculate something called a SAM number, the superaerometer number. And the SAM number is going to correlate to air void size distribution. I'll prove that to you coming up. The meter's also going to measure the typical air volume. So we looked at 95 different concrete mixtures, all kinds of different commercial air entraining agents, combinations of admixtures, different water to cement ratios, different slumps, different air contents in every one of them. We did that hardened air void analysis, the one that takes a long time. We're going to compare the SAM number to the hardened air void analysis numbers. Okay, does that make sense? Great, and that's what the data looks like. We have SAM number down here on the x-axis. We have spacing factor on the y-axis. This is the magic number, 008. And we see our SAM number of 0.2 does a pretty good job of parsing the data out. That means if your SAM number is greater than 0.2, your spacing factor is greater than 008, and this is no. This is not happy. This is not where you want it to be. And if your SAM number is less than 0.2, then it's less than 008 for over 90% of the data that's investigated. Again, this is able to look at the air void size distribution inside your concrete. Oh, that's lab data. How about field data? Well, here we go. We got some. 60 different field mixtures where we've done the exact same testing and we get the exact same trends. Again, great agreement here. This is the yes, this is the no. The SAM number does a much better job than the spacing factor. I'm sorry, it tells you SAM number does a much better job than the air content. It gives you an indication of the spacing factor. And just to put this real simply, if you remember the yikes graph I showed you earlier, this is the way we typically would try to run this test with just air content down here. Now, instead of air content, I'm going to use superaerometer number, okay? And we go from yikes, how do you specify this, to, oh my gosh, this is awesome. This is awesome. This means when my SAM number is less than 0.2, my spacing factor is less than 008. When my SAM number is greater than 0.2, my spacing factor is greater than 008, and we would never have been able to figure this out with just air content. Notice we take these two mixtures that didn't behave the same at all, but when we use the SAM number, they perform exactly the same. This is exciting. This is really exciting. We can look at freeze-thaw testing as well, okay? 666 testing. This is the one that takes 3.5 months to run. And again, the SAM number does a good job, at least with this limited data set, to determine between the ones that pass and the ones that fail. When SAM number is less than 0.2, pass the freeze-thaw test, greater than 0.2, fail the freeze-thaw test. So what are some observations? SAM number of 0.2 seems to correspond to a spacing factor of 008. Over 90% of the data is correctly separated with this limit, and the SAM number seems to correlate with the limited freeze-thaw testing. This is really cool. So how consistent is it? Well, over those 95 mixtures, we actually used 2 different meters, with 2 different operators, and ran them head-to-head. We're going to talk about air content and superaerometer number. If you look at air content numbers, the average difference is 0. 2 meters, side by side, 0. That's great. That's really good. And the standard deviation is extremely low. And again, if you compare the SAM number from 1 meter to the SAM number from another, the mean difference, again, is 0. And the standard deviation is pretty low. It's not perfect, but it's pretty low. So we need to add a new entry to this table. We need to add the SAM number. And in minutes, we're able to get the same information that used to take us 7 to 14 days. This is exciting. We can make decisions before the concrete's placed. We can save ourselves from a road that needs to be prematurely replaced. This is really exciting. So why is this useful? Air content is no longer enough to evaluate some modern concrete mixtures. The SAM number gives us a tool to make sure we get high-quality air void systems in the fresh concrete. It could be a useful tool also during the mixture design stage to help us understand how different admixture combinations come together. And it could be a useful tool in the field to actually troubleshoot the actual construction process. How do things change during hauling, during vibration, during pumping? Superaerometer can help us with that. So what's happening? How does this work, right? The last couple minutes, I'm going to talk about that. Well, the best way to show it is we took some bottles that were about 3 inches by about 2 inches by about an inch, and we're going to fill them full of air-entrained cement paste. Okay, so just no rocks, no sand, just air-entrained cement paste. And we're going to fill the rest of it up with water, and we're going to put a straw on it, and we're going to very, very, very carefully turn the bottle on its side. Okay, so we turn it on its side, and over time, bubbles are going to escape up and get caught on this surface. We're going to look at these bubbles with the stereo microscope. These bubbles are not inside the cement paste. These bubbles are floating in water. Okay, they've escaped. And we can use an air pump to simulate the pressures that would usually happen inside one of these pressure meters, and we can see what happens to the bubbles. And here's a typical data set. So we got bubbles, they're all over the place. That's atmospheric pressure. We go to 1, we go to 2nd pressure step. Oh, look at those bubbles. They look a little different. We go to the 3rd. We go to the 4th. Oh, and this is my favorite pressure step of all. I love all of them. It's like your children, but I love this one. Let's keep an eye on these bubbles right here. Whoa, where'd they go? Look at that. That's back to 4. Look at that one. Gone. 6, 7. As you increase the pressure, the bubbles are dissolving. Okay? This is Henry's law. We actually heard about this at one point in our lives. Okay? This idea that as a given pressure, that air will dissolve in the water. Okay? And that's what's going on. And when you decrease the pressure, some of the bubbles come back, but not all of them. Because remember, the air void system used to look like this. Look at all those bubbles floating around. And after the pressure steps, they look like that. If you can understand how these bubbles dissolve and come back, then you can understand the sizes of those bubbles originally. And that's how the super air meter works. It took us a long time to get there, but it's been fun. As you increase the pressure, you drive in the small bubbles into solution. When you pressure the bubbles the second time, there are less small bubbles, and so the concrete responds differently to the same pressures. So what else have we done? We've looked at hot weather, cold weather concrete. We've looked at all kinds of different aggregates. Okay, we've done a lot of field testing. We've gathered lab data from a lot of different folks. Okay, and this is really exciting. In February, we're going to have an AASHTO provisional test method on the super air meter. That is super exciting. That's really, really exciting. So that means we can specify it, right? It's going to exist. The following states have a super air meter. Okay, over 17 states do, and I've got 2 highlighted there. 2 states have already started to specify the super air meter on jobs. Okay, in Michigan and right here in Oklahoma. Oklahoma Turnpike Authority is starting to use it, and Bruce Arnold's starting to use it in Tulsa as well, right? That's right. Why don't we have more orange up there? We should. We should get more states. We should get more jobs, more people. And anytime I have a number next to it, that's the number of super air meters that are in a state, number of groups that are using a super air meter in the state. So we see a lot of folks are getting behind this. A lot of folks are getting excited about this. Again, started right here in Oklahoma with research. So how can this group help? Well, you can, number one, you can tell someone else about the super air meter. That would be great. You can try the super air meter for yourself. And we need to get the super air meters used. If you have influence on if they're used or not used, let's try it. Let's just see what happens, okay? I think it'll make your concrete better. In conclusion, data has been presented that shows that the air volume is not enough to determine the air void system quality in modern concretes, that the air void size distribution is much more useful. We've shown a novel test method that can actually tell us both the volume and the size distribution in fresh concrete. So a SAM number of 0.2 seems to correspond with a spacing factor of 0.008, and over 90% of the lab and field data correctly is separated by this limit. And the SAM number seems to correlate well with the limited freeze-thaw testing. And I want to share with you, again, superairmeter.com. SAMs are available. You actually get them off the website. And also, this is a pitch for my webpage, tylerlay.com, and this is me taking the ILS Ice Bucket Challenge, right? And of course, everything beautiful is orange, and I'm sitting on a throne of concrete. Yes. Thank you. Any questions?
So, you said that, so what's the good strategy of getting the right air content in modified, the air treatment in water reduced
So
concrete?
the right strategy is to look at your mixture up front and to investigate different combinations and see which one causes the least amount of issues. It's a function of the cement type you're using, the cement chemistry you're using, the air entrainer you're using, and the super plasticizer you're using, and the relative dosages of all 3.
So you don't have a magic formula?
I could give you a formula that would work for one set of materials, but anything practical would realize that I'm going to change every one of those every single day. And so that's going to change how it all works. I think the best thing right now is until we have more information is to measure, and then hopefully we can get to a point where we can make better predictions. Does that make sense?
So I guess in the beginning you would take maybe combination and see what works best for that
Exactly.
level of water reduction.
Exactly. Jeff?
Where did your inspiration come up with that?
Jeff asked me this question once before. So a long time ago, when you're poor and you're a grad student, and I went to eat Chinese food, I think in Austin, Texas, and someone was pouring me a bottle of water, in a glass, and there was, it's a great Chinese place, right? And so the glass is a little dirty, right? And so when they're pouring it on the inside, there was bubbles that were nucleating on the side of the glass, right? As soon as I saw that, I thought, I can look at the bubbles myself. And that kicked off the stereo microscope work, and that was a really important step in understanding this whole process. Chinese food.